A centrifugal impeller can throw air outward, but the wheel alone does not create an orderly discharge. The volute is the widening passage wrapped around the wheel. It collects flow, leaving every blade passage and guides that flow toward one outlet. Its geometry decides how much velocity becomes usable pressure, how evenly the wheel is loaded, and how much unsteady noise reaches the duct. Start with the cross-section. Near the cutoff, the passage is narrow because only a small fraction of the circumference has discharged into it. Moving around the scroll, more blade passages add flow, so the available area grows. A useful first design idea is nearly uniform mean velocity around the collector, but real designs also account for boundary layers, leakage, width changes, and the outlet connection. The energy conversion is not magic. Air leaves the impeller with radial and tangential velocity. As the collector area increases, mean velocity can decrease and part of the dynamic pressure can be recovered as static pressure. Recovery is never complete. Wall friction, separation, mixing, leakage, and a poor transition to the outlet consume total pressure. The complete fan curve must prove the result. Now focus on the cutoff, also called the tongue. It separates the high-pressure discharge passage from the low-pressure region near the wheel inlet side. Each passing blade sends a wake and pressure disturbance toward this edge. Blade count multiplied by rotational frequency gives the blade passing frequency, so under some geometries and operating points the cutoff interaction can become an important source of discrete tones and cyclic loading. Tongue clearance is a trade-off, not a universal percentage. If the gap is too small, blade wakes strike a strong geometric discontinuity, pressure pulsation and tonal noise can rise, and manufacturing runout or thermal growth leaves little margin. If the gap is too large, more discharge can recirculate toward the inlet region, weakening pressure recovery and changing the operating curve. Cutoff shape matters as much as nominal gap. A sharp edge fixes the interaction location but can intensify a narrowband response. A rounded, inclined, stepped, or otherwise modified tongue can spread the interaction in space or time. These treatments are not automatic upgrades. They can move noise between frequencies, alter recirculation, and change performance across the operating range. The scroll area law also has failure modes. A passage that grows too slowly can accelerate or choke the collected stream and create high wall loss. One that grows too quickly can diffuse too aggressively, separate from the wall, and produce a low momentum pocket. The designer therefore checks area distribution, width, sidewall contour, surface condition, and the local flow angle together. At the outlet, the collector becomes a diffuser and a system interface. Sudden expansion, an abrupt rectangular transition, a nearby elbow, or a blocked discharge can destroy pressure recovered inside the housing. The outlet flange size is not enough. The downstream velocity profile and swirl must be compatible with the connected duct, plenum, damper, or heat exchanger. Operating point changes the picture. Near the intended duty, the impeller discharge angle and scroll capacity can be reasonably matched. Far below design flow, separation, and housing recirculation may strengthen. Far above it, collector and outlet velocities rise and available pressure may fall. One beautiful computational image at one flow rate cannot qualify the full fan envelope. Real hardware keeps the boundary honest. This Longwell RDH housed centrifugal fan visibly shows the wheel, scroll, cutoff region, outlet, frame, and service geometry as one assembly. The drawing establishes physical dimensions for one model family, while the smaller single volute document shows a different scale. Neither image alone proves pressure, sound, efficiency, or a transferable clearance rule. A defensible design review combines simulation and test. Inspect velocity, static pressure, total pressure loss, wall shear, separation, cutoff pulsation, and outlet uniformity at several operating points. Then test airflow, pressure, power, efficiency, sound, vibration, temperature, and structural response with the production intent wheel, housing, motor, speed, density, and inlet-outlet arrangement. So what does a good volute do? It collects progressively, slows the flow without uncontrolled separation, limits backflow across the tongue, manages blade passing interaction, and delivers a usable outlet profile. Freeze the wheel and housing as a matched aerodynamic system, document the tested boundary, and judge every design change across pressure, efficiency, sound, durability, manufacturing tolerance, and the installed system.